Hey everyone, how are we doing? My hair is going all crazy. It's all sort of, but anyways, doing a bit better, coughing a lot less. Anyways, hope we're doing well. If you're in the chat, feel free to say hi. Little music. Madeline, good to see you. Probably got the email right there. We're gonna start with some confidence interval interpretation. Learn how to do those. Hey, Hannah, good to see you here. We'll turn on mute button. Might not give it any points, but he'll be here in the chat chilling with us. Good to see you, Ariana and Hannah and Madeline and Valeria. Good to see everyone. Hannah also in the chat right there. Gonna reply some emails a little bit later, give an exam, and do some interpretation. Looks like the green screen's doing better. We'll turn on the light right here. Give it a little more light. Does that work better? Maybe. It's not on right now. There it goes. We'll do what we're gonna do. What's up, Kaylee right there, and Regan and Tyler? How about we do some interpretations? We're gonna start with confidence intervals. And thank you everyone for being here, just swinging by. We're gonna focus a lot on interpretations right now. So the first thing we're gonna do is we're gonna interpret confidence intervals. So here we go, confidence interval interpretation. Ask a lot of questions, let's do this. Hey Hannah, good to see you there. Does anyone know how many types of confidence intervals there are to interpret? Who can tell me how many types of confidence intervals there are to interpret? So all I want you to do right now is tell me how many types of confidence intervals there are. Like how many forms of it we have. Does anyone know that? It's a good place to start, where you might have to do 3 different types of, there's really just one interpretation, but how many different things go in the middle, if you get what I'm asking? And one of them would be a confidence interval. So that's one of them. There are 3, great job Madeline right there. There are 3 that we've done. There's more in the world of statistics, but we've done 3 different types of interpretations. Confidence interval for the true proportion. Confidence interval for the true mean. Confidence interval for the difference between 2 means. Now we could even write true difference. We could write true difference. That's what we're trying to estimate. So there's the 3 types of confidence intervals that we've done. There are more, like the true difference between 2 proportions, confidence interval for the slope of a line, confidence interval for the intercept of the line. You can do a confidence interval to estimate anything. Confidence interval to estimate the true price of a steak. Well, that'd be on average, so mean. So with this, these are the 3 ways you've done it, and this is going to be important for the context of what you write. So try to put it in the chat for practice right now. I'm going to start writing it, but do it yourself because you will have to type this out for the test. So it's just good practice to write things like, I am blank % confident that the true blank is contained in the interval blank to blank. There it is right there. I am blank % confident that the true blank is contained in the interval from blank to blank. We're gonna highlight something right here. This portion right here is what goes inside of here, but it also has context to it. So nice job, Madeline and Henry right there. And I gotta say, like the grades I'm seeing from people, I'm seeing people who are doing great, getting near 100 in the class. Some people, I'm not gonna say who, there's people in this class who have over 100. Over 100. And it's people who are like coming to office hours, doing that work. If it's not you, don't worry. But I want you to know, if you want to sit here right now and you want to do the work, it's going to help. It's going to help to write these things down, practice. And I'm not mentioning anyone's names in the chat on who's who, but I'll just tell you, we see a lot of people show up here, a lot of people making great grades, and I'm really happy about that. So try writing these things out, try practicing. Great job, Henry and Madeline right there. The grades in the class are really great. Like, it's a really good semester. Great job, Charlotte right there, also practicing it. Love seeing that. And I should say, I want to mention this. We had some friends growing up, Charlotte. That name means a lot to me, Charlotte Bird, seeing that, the Birds, friends of family growing up. I knew a Charlotte Bird, so friends of family. I like seeing names. I'm like, I've seen that name before. I know that name. Okay, so we need to fill this out. Now, the easy parts, great job, Reagan, right there. The easy parts are going to be the % confidence. Usually we do something like 95, 90, 99, or things like that. And then the last part right here is the lower and the upper, and we'll show where to get these. That's the lower of the interval, the upper. So this is your general form. Good to see you, Olivia. There are things like we are blank % confident, or one can be. There's ways to phrase it a little bit differently. This is the way I like to phrase it, because I'm talking about me. I'm this % confident, or one could be is another way. So now let's go do some output and talk about what we have. Don't update. So with this right here, what am I making a confidence interval for? Let's do this right here and do this. I am trying to figure out what? Just think about maybe an hour-ish. We're going to do interpretations here. So what is this? What are we trying to interpret? What are we trying to think about what this question is trying to figure out? I'm highlighting this right here. You bet, Bailey. Always posted. Thank you for asking. So the true proportion, great job right there, because this is a categorical variable, the true proportion of rainy days. So since it's categorical, that leads to proportions. So here's a big note to have. If you're looking at what the context is, proportions are for categorical data. There's tools and techniques questions. So kind of, sort of, check over the review sheet. We'll put review 3 in the chat right here. Check over the review, and it goes over how there's tools and techniques questions, which are on the review page right here. I'll pin this. So check that out. Good question. Thank you for asking. And so now we know if it's categorical, note to take. I'm talking about the proportion right here of rainy days. So now let's go to analyze distribution. With this right here, we now have, let's look at the output and make sure we understand what we see. 301 is the amount of days it did not rain. 112 is the amount of days it rained out of 413, the total. What is this in notation? 0.7288. If I'm interested in not rainy days, is what in notation? So think about what this is in notation. We're doing some additional notes right here. Tell me what that is in notation. If you were to mark it in notation, could you tell me what it is in notation? I'm just going to take this right here and see if we can write it down in notation format. P hat, great job, Cameron, right there. P hat is a number contained between 0 and 1, representing the sample proportion, which would make this Q hat, which is the complement of the sample proportion. What is 301 now? It's not the true proportion. It's from a sample of 413 days, the proportion of days it rained. Colin, sending some Disney Stardust right there. Thank you, Colin, right there. You can make. I always tell stories about Colin because wanting to work at Disney, now works at Disney. Love it. X number of successes. This is technically n minus x, and this is n. What do you get if you add x plus n minus x? What do you mathematically get from this equation if you get x plus n minus x? You wouldn't need to know the other one's n minus x, but just think theoretically and what cancels. And be like, oh, if you add this number and this number, you get the what size? You get n. So that's not really required. It's just mathematically you'll get, like if you take sample size minus successes, you get failures. So we don't really call it n minus x in notation, but it is mathematically how it could be derived. We're just marking everything we can to make sure we understand. And technically the bottom one could be written as p hat plus q hat, because that's it right there. Now, if we wanted to solve this confidence interval by hand, we could do a 95% confidence interval, which uses slightly different calculations than JUMP uses. It'll come out very similar, but let's solve it by hand and then interpret it. We would go right here and do p hat plus or minus z star. Now, what's the point of the star, which is only used in confidence interval notation? And great job. And when would we use that one, Cameron? You are correct. Cameron wrote 1.96. And when would we use a 1.96 z star? So this last component, I'll write underneath it. This is the standard error. This is the confidence level. This whole thing is the margin of error. And this is the center or the estimate. It's the center / estimate of the interval. Just putting notation under what those things means. No, it's not a t. The z is used for, so z is used for categorical data. T is when we're talking Mr. T is mean. So this is not mean stuff. This is a one sample z proportion interval. And thus we use the z because it's a one sample z proportion interval. Sometimes called one prop z, one proportion z interval. And with this right here, 1.96 is the z-score for the 68, 95, because you cover 95% of the area. So if we go through and solve this, the mathematics we would get, if anyone wants to solve it and double check this work, it's going to be very similar to what JUMP will get us, but JUMP does slightly different formulas because different statisticians have different ways of computing this, but it's going to be very similar to what we'd get in JUMP. Let's go over to JUMP right here and grab the confidence interval by going here to the red arrow and going to confidence interval, 95%. And now we have our 95% confidence interval very easily. Okay. So if we had worked it, we'd get about, what is the confidence interval for no rain? So what is the confidence interval for no rain? You should be able to look at this output right here and tell me the confidence interval for no rain. You can just say from this to this, or you could do the full interpretation right now for practice. Remember, I can say all these things 1,000 times, but I want you to be able to recognize them. Don't memorize the z-scores. I got them memorized, but 1.96 is about the only most important one for a 95% confidence interval. We'll tell you the z-scores otherwise. Good, Cameron, good work right there. Be careful. When we get the lower and the upper, we want to go right here and right here for the one we're looking at. So you want to go across that level right there, so it'd be about 68 to 77%. Does that make sense? 68 to 77. Great job right there. Henry also writing it out. And then the last numbers there, check it on the last one right there. Oh, because you might have grabbed it looks like you have something a tiny bit different. And good practice. This is all practice here, remember. And if you make a tiny error, it's going to be just a point. So don't worry about it. Reagan, great job there. I am 95% confident the true proportion of days with no rain is contained in the interval 0.68 to 0.77. Now I want you to think about this. Here's what we can know. The full interval. And so we've already done our interpretation. Let me slow it down just in case anyone's lost, because the people here are following along, but if you're watching later, we said the percent confidence, I am this percent confident. And then we have to do the context, the true proportion, see how we have true proportion up there, of not rainy days is contained in the interval, and then we grab the lower and upper of the thing we're interested in. Usually over there is some sort of context, and we're not talking about the true mean, we're talking about proportion, because the percent or proportion of times it rains, so percent also works. But here's the thing. I want, with our rounded numbers, for someone to tell me the margin of error of this interval. It shouldn't matter. Tell me if the graders take off points. Please look over your finals and your projects. That wouldn't matter right there, percent or decimals. It doesn't matter. Doesn't matter. Tell me the margin of error of this interval. Someone tell me the margin of error of this interval, which is a good thing to back calculate. So here's the lower, here's the upper, 0.45, 4.5%, right? 0.045. Because if the full thing is the length of 9 divided by 2, and you get 4.5. Upper minus lower divided by 2 is the plus or minus. So plus 4.5 minus 4.5. And that makes the center of the interval about 72.5. And this is a rounded version of the problem. You know what's really interesting? If we go back and plug in our numbers, watch this. We're just going to round the numbers nice and neat for the time being. But I bet you the margin of error, we're just showing mathematically that we can get these numbers and knowing how to use formulas right here. Was it 401? Match this a little bit here. If I'm going too fast, please tell me. I'm trying to do as much as I can and show how to use numbers and formulas. We're going to round this for purposes, but it's probably not going to change it much. Okay. This is a rounded version. Please carry decimals if you're doing it. That just makes it look nicer on the screen. Okay, so 0.73 times 0.27 divided by 413. Square root is the standard error, times by 1.96, and pretty close, 4.3%. Not quite perfect, but kind of close to what we got using our quick estimates of what we were doing. 4.3 when it's rounded, 4.5 when we do it there, but very similar to what JUMP gave us with what the margin of error is. Any questions right now? That's a confidence interval for the true proportion. And I guess we should mention this. Who can list the 3 conditions for this? The 3 conditions would be condition number 1, you know it, you love it. You wouldn't quite be given kind of sort of Jameson, look at the practice test. Good questions. Random, 10%, and success failure. We'll be given p-values and then asked to interpret them because we can't use the applet. Kind of, sort of. We can give you a p-value and ask you if you reject or fail to reject at certain alpha levels. And that's what we'll look at here coming up. So I guess what we could do is to go in order. Confidence interval for true proportion is now we could do you want to do, should we do the test for the proportion next or a confidence interval for the mean next? Stay with confidence intervals or jump over to the proportion, which would be the same thing, but dealing with proportions. Take a vote right now. Let me put it in the chat, a vote. They moved around the YouTube thing again on me. So start a poll, test or confidence. Cool. We'll give it a half second here and whatever you pick, if we should do the test for the proportion or go to the confidence interval for the mean. And great job on the practice right there of which are the conditions. Oh no, vote now. We're ending the vote in 3, 2, 1. All over. Okay. And people have voted to do the test. Okay. Ooh, pretty overwhelming test. Okay. So now to do the test for the proportion, let's put that note here in the video so people can watch this again and see a test for the true proportion. Okay, so we're at currently 19. Oh my God, my right eye is like, I'm out today. Test for true proportion. When we do tests, we have something in our class called the HACS method. So the HACS method stands for hypothesis, annotate notation, check conditions, solve for p-value. Now I'm going to give you a pretty obvious one right here, and it's ridiculous. So if someone said, I think it rains, good to see you there, Olivia. If someone said, I think it rains 95% of the time. So just using, and this is a crossover question. Crossover question! That's our new thing. If someone said, I believe it rains 95% of the time, why would you not believe that value and could reject it? Crossover question here with confidence intervals and tests. Someone said, I believe it rains 95% of the time. You'd probably just look outside and be like, yeah, I don't think that. But then you can use the data to make the decision. I think it rains 95% of the time. It's not contained within the interval. It's not contained within the interval. Does everyone see that? 95, if we're, now I said rain. So if we look to the rain interval and we go here to it, it is not contained within the upper and lower interval, thus is a value that can be rejected on a two-tailed test with 1 minus alpha. Notice how this is 1 minus alpha, and alpha would be 0.05. Do you ever notice that with the jump output?
Wow.
Owen Wilson's impressed by it. So we could reject that value at the 0.05 alpha level on a two-tailed test because it's not contained within a 95% confidence interval with 1 minus alpha of the confidence level right there. So good stuff, and that's how we can know to reject something using a confidence interval. But let's say we're going to do the test right here. Now, the hypothesis, we always focus on writing the null hypothesis. So when you write the null hypothesis, it usually has this format, except for the last chapter. The format is going to be null states that some population parameter, we're going to abbreviate pop parameter, is equal to some hypothesized value. The alternative is going to be that the population parameter, we'll put something there in a moment. So when you're doing this, the alternative has 3 different possible signs to it. The alternative could have the sign, and make sure you know these signs, less than, greater than, not equal to. Now, how do we pick the sign of the alternative? How do we pick the sign of the alternative? How do we know what the sign of the alternative is? Kind of the context, the researcher's question. I like the, Valeria, yeah, definitely. We're not going to points today, but that's a great answer. We'll throw you a nice wow right there. That is true. The context, the researcher's question, it's not the data though. We don't look at the data and let the data decide what we're researching. We ask, okay, what do we want to understand? What is our hypothesis? And we'll have one here in a second. So you might tell your friend, I think it rains less than 95% of the time. So with that hypothesis, then what would be the sign of your alternative? You say, your friend says, I think it rains 95% of the time. You say, I think it rains less than that. So you collect data for 401 days or 413. So you are the researcher and you collect a lot of data, 413 days of data. Your friend says, I think it rains 95% of the time. You're like, I think it rains less than that. And then you collect data after you've formulated your alternative. What would be the sign of the alternative? Not a trick question. If you're like, man, that sounds too easy. Your friend believes it rains 95% of the time, and you think it rains less than 95% of the time. What would be the sign of the alternative? Thoughts on that? Cameron got it right there. It's less than. You got it. All the answers today. Great job. So the big thing we need to know before getting started on this, and we're kind of making two different sheets here right now, is what kind of test are we doing? There's how many different tests that we learned. Be careful. How many different tests, and can you name them? Because they're all slightly different with slightly different conditions. They have similarities, and they can all be done with the HACS method. But do you know how many tests we learned this semester at the end of the class? And there's more, like a test for the mean, a test for the slope. Right, great job right there. There's 4. Test for the true mean. Test, or we could do start from the beginning. Very good place to start. Test for the true proportion. Test for means. Anyone know the last one? Last one's the last one we did, one of my favorite chapters, because it just seems easier than the rest. What is the last one right here? You can call it a test of the, it starts a little bit different. Just practice so you can remember, and you should have some ideas what these things are. Chi-squared test of independence. I don't know, we call it chi-squared, or it's actually more like you do a little, that squared test of, whoa, still in the superscript. Test of independence. It's a chi-squared right there, not chi. It's so, brain. Independence. There we go. Can't spell independence. People call it chi-squared, and I'm like, sure. So right here, you have to know what you're doing, because when you write this out, I'm blanking on what to find for pop for some reason, pop parameter. So the population parameter is going to be based on the context. PO? We'll talk about that here in a second. You got it. This right here is going to be, you know what we could do? Watch this. This might help with understanding what goes with what. We'll put this over here, and the population parameter is going to be either P, it's going to be mu, or mu1 minus mu2. That's the thing we're interested in understanding. That is P, mu1 minus mu2. And we're going to put this down here for the last one because we're not going to do it for the last one. That does not mean the 0 or null set or something goes in the last one. We're going to write it differently in a moment. But you know what? I really should put this on the other side because it's going to make more sense if I put the blue over here. Let me just rewrite this. This is P. This is mu. This is mu1 minus mu2. And we're not going to do this format for the last one. Over here on the other side of this, we're going to put a green mark. And we're going to highlight the hypothesized value in green. What is the hypothesized value when we test the proportion? What is the hypothesized value when we test the proportion? Like the believed true proportion that is stated by a problem according to the null. What is the hypothesized value according to a test for the true proportion? So this is a good, Cameron right here, good question, wink, wink. So what is the believed hypothesized value when we test a proportion? A hypothesized. P0, which stands for the hypothesized proportion. The naught right there goes with the null, so it's the hypothesized proportion. And then mu would be mu naught. Now technically this is delta naught, but usually delta naught is equal to 0. I know it's weird, we do delta, but it's like difference between our change in. And so usually this is 0, and we're not going to do this format for the last one. If you're wondering about the format for the last one, which I should put an addendum right here, we'll put here chi-squared. We'll do it the right way. Chi-squared. What is the format for chi-squared which doesn't follow this format that we just wrote? What is the format for chi-squared which doesn't follow this format we just wrote? We just write the null states that x is independent of y. The alternative states that x is not independent of y. So now you have a really good note sheet right here. Great job, Valeria, right there. Jameson, great work too. The null right there, it's more of a sentence. We'd say that X and Y are independent is the null, and the alternative would be that they are not independent. So we'll write first 3 chapters, or first 3 tests, because they're different chapters. So make sure for the first 3 tests to use this format, and for the last few, don't. And to make it even more clear, let's just put the bands going like this, and go like this, and then do a little like this for this, and do that right here. Okay. Color coding to help out, to let you see what is what. Don't use the format that we have for the first ones. I'm sure there is some way to do it, but there's lots of ways to do things. Okay, with that, we now understand the hypothesis, but let's see if we can do it. So in practice right here, what we would do is we'd take some output, and we'd go here to a test on a probability, which is testing the proportion. Put it a little closer so you can see it. So we go to test proportions right here, test probabilities, and we go in and we write 95% here. It should auto fill out the 5% for us, and now we have it. Now we automatically get the results of the test, and it's done a little bit differently than what we would get. This is because this is actually using the chi-squared. We're going to do it ourselves here in a second. But look at the end result of the test using a Pearson chi-squared test on proportions, which is not exactly what we do. JMP does a little bit different. But if you are testing this right here, what would be your null hypothesis about the proportion of days it rains? Use this output to tell me your null hypothesis about the proportions of days it rains. Use this output right here to tell me your null hypothesis about the proportions of days it rains. Use this output right here to tell me your null hypothesis about the proportions of days it rains. So remember, we can look right here and see hypothesized probability. So use this output. Then if you're talking about proportions, what would go in the blue region? Scroll up, see. Try writing this out. Try writing the null hypothesis. That's all you need on the screen right there. Things are color-coded for you to help out. Color coding on the screen, really helping out right here. Think about what you have as your null. Write out the null hypothesis for this. If you're going to interpret tests, you always have to be able to write the null. Null has the equal sign. So how would we write the null right here? Close, Cameron. Try full notation. That's basically it. But we're missing some notation. You're really close, Cameron. And we wouldn't put 0.95. We could put 95 or 95% or 0.95. Very close, Cameron. Really close. Give it another. You got it. I mean, write the full thing. I see where you're going. So the only things that can go in here are going to be P, mu naught, or mu1 minus mu2. The only thing that's going to here will be the value of P naught, mu naught, or 0. Great job, Lucas. That is correct, Lucas, right? No, Lucas, be careful, though. There's one error, Lucas. I want to see if you see it. Cameron, you still have an error. You're saying, which is true, but that's not the null. You've said that the null states that the null proportion is 95%. You have right now the null states that the null proportion is 95%. See if you can catch the small error. Great job, Valeria. That is it right there. The null states that the true proportion, there it is right there. The null states that the true. P naught goes on the other side. P naught is the value of what you hypothesize. Does it make more sense seeing the color coding and now seeing it? And that's why I want people to always do it, because I can say it, but I want you to see it and be like, oh, the null states that the true proportion is equal to, and you can put 0.95 or 95%. If you put 95%, I wouldn't count off. And that's where if a grader counted off, I'd want you to tell me. But hopefully seeing the color coding and working this out right there, really good practice to do it. And you'll just select from underneath pop parameter, and you'll also select from hypothesized value, but plug in that hypothesized value. Now, if we were to do this by hand, what would we have to do? To do this by hand, we'll just, we talk about the p-value here in a second. But doing this by hand would require the following. We need to write out, it's not so much the alternative, it's the null, it's not really the alternative, it's just the hypothesized value. And then the alternative would be p less than 0.95. So p naught is the hypothesized value, hypothesized probability in this instance. Good questions, Cameron, good stuff. And now we'll write out here p hat minus p naught over p naught q naught over n square root. And we get a z-score from this. And with this, it's going to be, we're going to round some numbers. 27% we're going to say. Can anyone find this z-score before I find it? See if you can find it, p naught right there. Can anyone try to find this z-score for me? And 413, right? Let's sign up this z-score. 413, sample size, just so you can remember, is 413, I believe. If you're wondering how we got n, check out the previous slide where n is right there. And we also marked it over here in our previous notation. These are not p naught and q naught, though. If you're wondering how I know p naught and q naught, this is p naught, this is q naught right there. So now, there's the notation. P naught, Q naught over N, P hat minus P naught. Check it out right here. And let's go solve it. There we go. And that's the standard error. Oh my gosh. You know what? The z-score is going to be close to 66, I think. I think it's going to be close to 66. Negative 66. Negative 67. I should have guessed that. So do you know what this means visually speaking? This means visually speaking, we landed all the way over here on the normal curve. Our p-value is this area. This over here is the middle 99.7% of the curve. What do you think our p-value is when we have the area less than this, which is we're going to graph to the less than because our alternative hypothesis was that the true proportion is less than 0.95. So that is how we know which way to graph, because the alternative shows you the direction you're going to shade. Our p-value is basically what? What do you think our p-value is? What do you think the area is below the curve when 95% of the area is contained within 3 standard deviations between -3 and +3? Insanely small. We're so far off the curve, we can't even see it. So at this instance, we're saying to our friend, what you've asked me to believe is virtually impossible given the data I see. I reject it with the utmost certainty. I have the strongest of evidence right here. So this is a z-score we could give you where you would have to know the answer because it's so far off the curve. Always try to do a mini drawing. We usually give you crazy z-scores or z-scores that would be towards the center, like a z-score of 0. Not exactly that, but close. So now that we know the p-value here, we annotated our notation. We didn't check conditions. Success failure, we'd need to check, which would be p naught times, or n times p naught, and n times q naught is greater than 10, greater than or equal to. Brock knows.
It doesn't matter.
If it's 10, don't worry. We won't do that to you. So n was 413 times. The interesting thing about this, you only need to check the what of the whatever of these two values. So while I'm solving this right here, you only need to check. I'm gonna do an about equals, and it's about 20. Close enough. You only need to check the smaller, exactly. And you can, I'm just doing a quick round, like 5% of that. If you want to get the exact numbers, they're both greater than or equal to 10. The smaller one would be the only one to check, and it's 21 rounded up. So we could round it, get the numbers. That rounds up, that rounds down. There you go. So they're both greater than or equal to 10. Technically, you only need to check the smaller one, so we're good on those. That means we can run the test. And now that we check conditions, let's interpret the p-value. The p-value here is equal to 0. We would probably give you this in output or let you know, and that is p-value, that's not proportion, that's a p-value. You should get this on a test, and it should be indicated to you. In the output from jump, the p-value was indicated to us right here. So there's the p-value right there. And to do the same color coding, we'll just do a little bit of that right there. And the p-value is not that. That's just telling you how much area was between there. Long story short, we passed the success failure, exactly. So now we have to get to our interpretation, which is the main thing you should know how to do, and a lot of people have trouble doing, understandably. So now we say my p-value, let me write this instead. I blank, try to remember how I write it to make sure you can write it. I reject, do not reject, or I'll write fail to reject. No. The issue I'm worrying about is that lots of instructors and lots of different graders, and I want to point this out, fail to reject is just an old way statisticians talk. If I tell you I failed to go to the mall today, what am I telling you? I'm going to write failed to reject here in a second, because that's the classic way of doing it. But if I tell you I failed to go to the mall today, what am I telling you? I failed to go to the mall today. You say, did you go to the mall? And I say, I failed to go to the mall. I didn't go. So what I prefer to say is we reject or we don't reject. Now, what is the bad word we don't say? There's a word we don't say in here. You can put some asterisks on it. But that bad A word we don't say. You say it like, oh no. We don't say this. We don't say accept. Exactly. We don't say I accept. We either reject it or we don't reject it. Don't reject right there is the same thing as saying fail to reject. So we'll put fail to reject. I just don't want anyone to lose points if on their final they put don't reject and their teacher's like, oh, excuse me, it's fail to reject. I'm like, it's the same, it's just an old way of talking. I reject, I fail to reject. There we go. The null with a p-value of blank, which is smaller okay. I reject the null that the true portion of days it rains is equal to 95% with my p-value, that's just basically 0, which is less than my alpha of 0.05. This is evidence from an alternative that it rains. Great job right there. Yeah, I didn't put out. That's a Cameron. Cameron, great job earning a wow right there. Cameron, that would do it. Good practice, Cameron. That has everything we want. Just throw in the alpha right there and you should be good. And we're going to highlight and show how Cameron did this. Try doing it yourself if you want. So try doing this yourself right here. Let me make this a little smaller. I just don't like this wrapping the p-value text. That looks good right there. Okay. Smaller. Oh my God. And if anyone else wants to practice right here, practice. Okay. There are other ways to do this. I try to do it about the same way every time, but you have to have these components right here. I reject or fail to reject. Oh, no, that's correct. I thought I said I reject to reject. I reject or fail to reject the null. Choose one of those with a p-value of state your p-value, which is smaller because, and I want you to notice this, there's really only two paths to go. You either go down the path of rejection, which is this path right here, because your p-value is small, and then you have evidence for your alternative. Or if you fail to reject, because your p-value is at or larger than alpha, you do not have evidence. So I put them on the same side of it to show you you're either doing one of two paths. You'll either reject the null with a small p-value that is less than your alpha, and you'll have evidence for the alternative. Or you will fail to reject the null with a p-value that is at or larger than alpha, and you do not have evidence for the alternatives. Everyone, does this make more sense seeing this right here? And just taking a look at it and seeing that there are only two paths in this decision. I reject the null because my p-value is smaller than alpha, which means I do have evidence for my alternative. I fail to reject the null with my p-value, which is at or larger than alpha. And if it's larger than alpha, you can just say larger than alpha. This means I do not have evidence for my alternative. Because if you fail to reject the null, you still believe it. It doesn't mean the null is true. It just means you didn't have evidence to go against it. Great job, Valeria, right there. So with this, Cameron so perfectly did this because we need to know our null. And now we need to know our alternative. So, and we need to know p-value. Oh, it's less than. And p-value is basically 0, and alpha is equal to 0.05 unless stated otherwise. The test does change alphas with questions. So we'll highlight these things. P-value just goes into this spot where p-value is. Alpha just goes into this spot where alpha is. And the null, make sure to write it out. We'll circle it in purple right here. The null hypothesis. Perfect. And then alternative hypothesis, a light purple. So try writing this out. Nothing beats writing these down, knowing how to do it right there. Looks like the purples are too similar. I'm just going to change up a purple color. So once again, write these down. We'll do some rainbow color on this right here. Rainbow color. Didn't do enough rainbow color. That's rainbow color. There we go. So the null right there, I reject the null that states the true proportion is equal to 95%. The true proportion of rainy days is 95% with a p-value of basically 0, which is smaller than my alpha level 0.05. This means I have evidence for my alternative that the true proportion of rainy days is less than 95%. Good work right there. Okay, so now we're now going to do confidence intervals for the mean. Oh my gosh, that was a long segment. In these next segments, we'll go faster. So a confidence interval for the true mean, we need what kind of data to do confidence intervals for the true mean? To do a confidence interval for the true mean, we need what kind of data? To do confidence intervals for the true mean, you need what kind of data? Quantitative. We could make histograms, box plots, dot plots, all those great things right here you see under this. That'd be categorical. We just saw some bar charts, but we're now doing confidence intervals for the true mean. So we're going to make some histograms, dot plots, box plots, any of those can be made. So let's go here and analyze bike demand. So now when you think back to our sheet, we are trying to understand the what of bike demand. We're now trying to understand, like if you talk to me, you just say, hey, Brian, we're trying to understand the what of bike demand for our data. Just use the words we have right here to think about the context, the true mean of bike demand. Like on average, what is bike demand truly on average? Like what's the true average bike demand? What's really cool, and I just want to do this as a segue, what you can do in statistics is I could actually go over here and do the following, and just showing this is a little above everything moment. What do you think I've done right here? This is way beyond our class for the moment. But what do you think I've created for every day? Which might be important, and I just did it in a second. Which actually, it's what we're doing, but just 7 times. I've actually just created a what? I've created confidence intervals for the true mean of each day. This was done via an ANOVA analysis of variance, but now I have confidence intervals for the true mean bike demand on each individual day. Like the true mean bike demand on Monday, the true mean bike demand on Tuesday. So we actually use this data. It's just now we have 7 confidence intervals, 1 for each day of the week, because there's variation within the days of the week. And it can also be shown here with side-by-side box plots, but the variation between the days of the week doesn't look to be statistically significant right there because of the high p-value. So anyways, that goes a little bit beyond, so I'm going to go back, and just do demand, so we can talk about one quantitative variable and only look at a distribution of the mean. So analyze, demand, here we go. And everyone see we have a histogram. Now, this couldn't be better for us for conditions that y. There should be no question on condition 1, randomly selected data. Condition 2, less than 10% of all data, which is less than 10% of all days that exist. So I'm sure 413 is less than 10% of all days that it could exist because there's infinite days. But condition 3, the nearly normal, doesn't say that that has to be perfect. But if our sample size is large enough, it could be a little skewed. This isn't even a little skewed. Our data looks basically what? Like talking about the nearly normal third condition for confidence intervals or test for the mean, after we pause, our data looks normal to begin with. So via the central limit theorem, the distribution of the mean will be even more normal. And so if you're wondering about that when I say those words, like via the central limit theorem, the distribution of the mean will be more normal. It's because the central limit theorem applet right here that we use to show this, the applet just shows the theory behind it. And our distribution has a little bump on the right. So we could pretend, here's our data. Looks like this, a little bump there on the right, about like our data. And if we do the distribution of means of a very large sample size, even larger than this will do, we can see what will happen as we take means. And repeating this process, making these blue dots, will show us that the distribution of the mean looks even more tighter and more normal. I wish I could do more granularity on these bins, but it is more normal, I promise you. It's just that the bins look a little bit weird. And with a very large sample size, this will be even more normal. The bin sizes didn't work perfectly for me there. So with that in mind, this is important to know all the output in this interval. Here's go away. Oh my gosh. Mubot, go away. I need to know any of the notation on this screen. What is some of the notation? We'll just go right here and do it again. Any of the notation on the screen. Any of the notation. Oh my God. Sorry to interrupt, but I had to graduate last spring and popped a feed in this year. Oh, thank you, Credible Tube. Yeah, I remember you right there. Dude, Credible, so good to see you. Thank you. Get a little
Wow.
Owen Wilson wow for you right there. I appreciate that so much, Credible. I do remember you so much. Thank you for all that positivity. I'm going to answer some questions now. I really appreciate that. It's very kind of you to say. I want everyone to learn. That's always my goal, and I want people to use this. Hope you're doing well in your career or graduate school or whatever you're doing in life. But thank you so much. I like all the positivity. And we got the notation mark now. The sample mean is equal to this. The standard deviation is equal to this. The standard error of the mean, SE sub y bar, is equal to this. This is the lower for an interval and the upper for an interval. And so we have all the notation. That's just a U for upper and L for lower. So there we go. And we could find this out ourselves if we wanted to do the 95% confidence interval. So a 95% confidence interval. Thomas! Yeah, did you win? We might have an extra Kahoot shirt. Did you win? If you did, swing by, and let me see how many I have. I might have an extra one. So yeah. So Y bar. I got third. Yes. Come by. Swing by here. I could even, if you come by while I'm doing this, just come on by, knock on the door, tell me your size. I'll see if I have it or in your size or someone you want to give someone, and then swing by, grab it, and it's yours. Oh, does anyone know the degrees of freedom for this? It's over there on the side. Don't know the degrees. Great job, Cameron, right there. DF. We could write 412. That's a DF. A lot of people think my Ds look like O's. I mean, they do. Oh, is that Thomas? One second, everybody. Add some visitors, awesome stuff right there. So I love it. I was like, hey, you're here. Boom, got here. So with that right there, we now have to input the formula in here. So they said study hard and all that stuff, so you didn't actually get to hear them. Let's put in the numbers, 4,802 plus or minus. Now the T star, does anyone know what it's going to be? I can tell you about what the T star is going to be for 95% confidence. Does anyone have a guess on what the T star is? I think my audio is going. It is, right? There it is, good audio. Now we could go find it, but remember we're doing 95% confidence with 412 degrees of freedom. I have an idea of what it would be. Does anyone have a guess of what the T star will be? Before I go find it, does anyone have a guess of what the T star will be before I go find it? We have 412 degrees of freedom, 95% confidence. I have a guess. I want to see if anyone else guesses what I guess. Don't look it up. Just tell me what you think it's going to be. Tyler, 1.96 is basically right. And great job right there. Cameron, yeah, I think so. We'll see it here, and you can use the SE. Standard error. I'm going to guess 1.962, which is basically that. So let's go here and input this. 412 degrees of freedom between, and it's 1.966. You notice I wasn't perfect. It's 1.966. Pretty close. It's probably got like 1.962. Watch this. I feel that too afterwards. Oh, 1.9657. So it's very close to 1.96. 1.96 would basically work. So you know what? Here, we'll write 1.966 because we don't want people to think we're using the z-score. And then the standard error, which is s over square root of n, is already found for us, which is going to be 86. We're just going to round it for rounding purposes for the time being. Carry decimals when you do the test. It's just easier to read things on the screen when they're not rounded. 86 times 1.966. What did we just find here? What did we just find by doing 1.966 times 86? So that was the t times the standard error. I'm hovering it over what it is. We just found the margin of error. So remember, this is the margin of error right here. Everything after the plus or minus, 1.69. And what you can do right now is you could take this and add it to 4,802, and look, you get, and it's probably because we didn't do the decimals, you get that number right there. 4,802 minus, and you get the lower. Is this making sense that we have now shown that the jump interval right there is calculated correctly? They carried more decimals than we did, so their numbers are a little more exact, but you should be able to find it and find these values. You can plug in s over square root of n and get the standard error yourself, 1753.2576. Square root of n is like 20.6, or close enough. I didn't have the square root of n ready, so there's square root of n, and 1753. There's s over square root of n, and that's standard error, which is already given to us in the output. Puppet Shark, yeah, right there. Do you guys like students? They were like, is the camera on? And I was like, yeah, you want for if you want. You'll just appear on stream. So they chose to. Tommy and Tommy swung by. I like it. So with that, doing so well. But yeah, just tiny bit, a little bit of a nasal drip. Fun times. So with this right here, what does this interval mean? I think this is the easy part. The easy part. So what would we have right here? We are trying to interpret the true mean of rainy days. So you can use this interval right here, try to write it out, give it a moment in the chat. Can you write it out? Try writing out the interval right here. You want to start out with the IM. I'll circle the things here. Try writing it out. The more you write it out, the better you get at it, the more you know where to look. I am 95% confident that the true mean, not of rainy days anymore, the true mean of no longer rainy days. This is the true mean demand of bikes. So I was writing that last moment right there, but this was demand of bikes. Last one was rainy days. This is demand of bikes. That would only be like a half a point off or something. Don't worry. You got the majority of it. If you notice, it's right structure, percent confident, true demand, true mean demand of bikes. Exactly. I am 95% confident that the true mean of bike demand is contained in the interval blank to blank. Exactly. Good work right there. So that's got confidence intervals for the mean, and we went over the output and the formulas and the conditions, all these things right here. Now we're going to go to testing the mean. Let's go here to testing the mean. I'm gonna start playing the Resident Evils over break. Resident Evil 2 remake. That's fun. Okay, what video games are you gonna play if you're gonna play a video game? Maybe people are gonna play like Valorant or League or something like that. Here we go, we're gonna test, and I want you to think about this value I'm testing. Would you reject this value or not reject this value? So crossover question here again. Where's Tommy Squared? They were just here. Skyrim, yeah. Skyrim came out in 2011. You know how I know that? Do you know what the release date for Skyrim is, Cameron? Look it up, and it's not hard to forget the release date of Skyrim if you know it came out in 2011. 11/11/11, release date of Skyrim right there. Very easy one to remember from release dates of video games. I think it's around GTA 5 came out. GTA 5, I think the highest, quickest selling grossing game. Tommy Squared, love it. Yeah, Skyrim is a good game. I need to play more like Fallout New Vegas though. That's good too. I think it was 2013. That was 2013. Oh, is GTA 5 20? Sounds about right. GTA 6 preview 2025. Saw the preview. Huge preview. Why would you believe or not believe 4,950? No, GTA 5 was not 2018. Not 2018. No, it's October 1st, 2013. Yeah. No, it's 2013. It meant to come out next gen 2018, but 2013 is correct. It was 2013. I've got it up here. GTA 5 is 2013 right there. I was like, no, not 2018. Yeah. I was thinking through the timeline of games. I was like, sounds about right. Yeah, over 10 years ago. Still crazy selling. Why? I'm bringing this back right here. Why would you believe this value or not believe this value? This value on the screen, as I bring us back, I distracted us too much. Why would you believe 4,950 or not believe 4,950? I am. And Cameron sees right there, 95% confident the true mean demand for bikes is contained in the interval, and that value is in the interval. That means we think it's a possible value of the truth with 95% confidence. So that means when I run this, you would expect your p-values to be a little bit higher or a little bit lower. Would you expect your p-values to be a little bit higher or a little bit lower? Lower p-values lead to the rejection. And we're going to ask on a two-tailed test for this. We're asking, is it that value? Is it not that value? And Cameron said higher, which is true, which means don't reject the null. So let's go over here, click OK, and we do see higher. One of them is low, but we're doing the two-tailed test, which is higher. I didn't choose something to center of the interval. Let's go grab this and talk about what this output means. Okay. So we're going to go over here to our test page. And here we are. Why am I so congested? No. Really? So close. I'll erase all this. I said erase. Okay. There we go. What in notation do we have right here? I know, I don't like saying fail to reject. I don't reject. What do we have in notation over here? What is any of this stuff in notation? What is any of this stuff in notation right here? So think about any of it. It changed the word on, I don't like it says actual estimate, an estimate of the truth. So what is any of this stuff in notation? Any of it in notation? Thoughts? Mu naught. And it's too big. Mu naught, hypothesized mean. Y bar is the estimate of the truth. Degrees of freedom is obtained from n minus 1, meaning that n was equal to 413. Backworking it. Standard deviation is S. Standard error can be achieved by S over n, if we want to get it. Square root of n, excuse me. That's for square root of n. Not really sure how to explain it. But the t-test? The heart blocks a little bit of the screen. I hate that. So I can't read that last word. I'm going to do a dot so I can see it. Yeah, you know the t-test? Great job, Jaden, right there. So now, when you're doing a hypothesis test, you always want to start by writing your what and your what. And see if you can do it here. You want to start doing a hypothesis test by writing your what and your what. So start trying to do it, see if you can get it here. And yep, try doing it. Give it a shot. Null has the equal sign. Alternative is based on the researcher's question. We're seeing if it's not true. That's a hint. We're seeing if it's not this value. The null states that the true mean, great job Cameron right there, wrote the null. The null states that the true mean is equal to 4,950. Then all you do for the alternative is you change the sign. And we're seeing if it's not equal to this value, so the true mean is not equal to 4,950. That's all you do, is you just change the sign. Mu is not equal to that value exactly. And so now when you look at this right here, the t is what comes out of the test. Jump has already done a lot of the work for us that when we do this, whoops, wrong value. If we do the t-test with this, we will obtain this value. We're just gonna back work and check Jump's work over here. Put a little box where we do the t-test right here. The t is equal to, with n minus 1 degrees of freedom, y bar minus, and I'll zoom in so you can see a little bit better. We're just, I mean, yeah, kind of. We would do this by hand if we didn't have a software. So we are we're not, yeah, Jaden, you're right.
Wow.
We are kind of doing that right now. We're understanding, we're making sure we know what the output is, and then we're testing our knowledge if we can write the test. So we need to plug in the values right here. So basically it's like, would you know what to do with this output? And then you can confirm just by checking this that it works. To be like, okay, I got the same value as Jump, so I'm doing it correctly. And we're not carrying all the decimals, which I would suggest carrying for the test. So we should get the value, and we'll just confirm it works. There we go. And here we go. So 4802 minus 4950, that's that value, negative 148. And now 413 square root 1753.6 divided by the square root of that. Forgot what the top is, so we're just going to do it again. It was 148. And there it is. So there is the value. Jump might have carried a few more decimals. Thank you, Cameron, right there. Good to see you, Alec, in the chat.
Wow.
You can always combine. We'll throw an Owen Wilson while for you right there. So negative 1.715. Now, where the negative 1.715 is actually right where that line is. Now, notice we are going to do the does not equals alternative, which is going to be this one right here. This is the greater than, this is the less than. Some classic Jump questions will do things like deleting off one of these values and then asking you to find it. How would you find this value? We're hitting a ton of stuff right here. How would you find that value if it was deleted from the output? So what we're pretending here in this question is you're given Jump output and you're missing a p-value. Your less than p-value is missing. So how would you get that p-value for the less than test? And great job, Cameron's already said it, is the less than and the greater than add up to 1, so they would be complements of each other, 1 minus the p-value. But what about if you were missing this p-value up here? Then how would you get that p-value? So that p-value is now missing, and great job, Cameron already said it, it's 2 times the smaller p-value. So it's the doubling of this on the other side visually, to where if you had this down here, you would double it, and this is what you're looking at right there, is the doubling of the smaller p-value. You just do 2 times the smaller of the ones, so 4.4 is 8.8, there you go right there. Jaden sees it, so Jaden's like, oh, that's how we're getting it. Just double it. When I found out how to do that, yeah, I know, you're just like, oh, it's just all the other, you just reflect it on the other side, it's just 2 times it. And then when you see it, you're like, oh, it's the does not equals is on both sides, like we're testing, it could be larger or smaller. That's why it's does not equals. Well, what if it's larger? What if it's smaller? Either side of the curve. It doesn't matter. The answer to the question. I need to make it so I can hear the sounds. I'm mishearing them too. I'm just doing them from memory, memorizing what they are. So now we have the t statistic. We have the p-value from the output. We would have to give you this output in this instance, usually for you to get a p-value. And now that we know the p-value, we can go down here and interpret our result. We're going to grab just this output right here and go down to our result of the t-test and use this. Okay. Well, we can just go to here. So we're going to rewrite what we have, try to interpret this as I write this out. We'll do a different one. Try interpreting it. We'll do an alpha of 10%. Why not? No, we can't. Oh, sure, why not? If we do an alpha of 10%, it changes the question. Sure, let's mess with it. Nah, because we had it coincide with the previous results. Okay, we'll change alpha next question. Because I said we wouldn't reject it, but that's on a two-tailed test with 0.05 alpha. So... give it a shot. Your time to practice right here. This is our time down here. Going strong, lots of tests. Big review session right here. I'm doing more than I wanted. I was just going to come on and mention the things, but I was like, you know, I got a lot of energy. I haven't done a lot of streaming lately. Hopefully this helps some people on their test. Yeah. I realize people usually watch the most recent stuff on my channel, so I was like, let's do it. I've usually done this. I usually do it Twas the night before, and I do it during the night, but I don't have my computer in my house anymore, or in my apartment. I'm in a house now, but apartment back then. I can't do night streams. So maybe one day again, but having a computer at home leads to too much work. It's funny, I think I was a better teacher when I had my computer at home. I had a better worse home life, because I'd just stay up some nights like 2 a.m. or just like not hang out with my wife and do work. You need to hang out with your wife if you have a wife. So try to interpret this. I'm just talking and filling the airwaves. It's your chance to interpret this. If you're watching this in the future and just hearing me going on and on, you can pause or mute the video until you see me move around and do something different. But see if you can interpret it, because that's the real point of this. I erase the coloring on alpha. I reject and null that the true mean of demand of bikes is equal to 4,950 with a p-value of 0.088, which is less than my value. Oh, yeah, you did that. Cool, Cameron. Yeah, you can do it that way, because I changed alpha, didn't I? This means I have evidence from alternative that the true mean demand of bikes is not equal to this. Yep. And if you use that alpha, you would reject. If you use the alpha I have on the screen right now, you would not reject. Notice how you made the test more powerful by increasing alpha. No, that's I changed it on you, so you did it correctly, and you made the test more powerful by increasing alpha, which gives us a chance to mention that increasing alpha increases power of the test, decreases type 2 error rate. Concepts we should also know right there, like increase alpha, decrease beta, increase power of the test. But you increase your type 1 error rate by increasing alpha. So just review concepts that alpha is type 1 error rate. We only have a few more things right here. Well, we did the test for the true mean. So now let's do the next one. Confidence interval or true difference. Okay. So the confidence interval for the difference between two means. What kind of variables do we have when we do the confidence intervals? Great job, Jameson, also. I fail to reject the true mean of bike demand is 4,950 with a p-value of this, which is larger than my alpha 0.05. This means I do not have evidence from alternative that the true mean demand of bikes is not equal to. Great job, Jameson. Good work. All the wows in the chat today. When we do the two sample t-test, what are the two variable types? A lot of people get this confused. Is it quantitative, quantitative, categorical, quantitative, categorical, categorical? What kind of variables are we working with when we test two means? We test their difference. When you test the difference between two means, it's categories and quant. Why is this? Because we need two means. Let's test to see if on rainy days, there's less bike demand. So we go here to analyze, great job Valeria also, fit y by x, and now we go to weather as the explanatory variable on the x-axis, and we go to demand on the y-axis to see if rain somehow explains demand. I always like looking at jump output this way and saying, does weather explain why we have certain demand? And we click OK. So now we go to t-test right here, which also does the t-interval. And here we are. Once again, know your output. So the top of the output is side-by-side box plots, and then the bottom of the output is the t-test. More importantly, it's a t-test with unequal variances assumed, which is the Welch's t, which has complicated degrees of freedom. The degrees of freedom would have to be found using a degrees of freedom calculator. We could do that right here if we really want. So this is, if you really, really wanted, you'd have to go and use the output for each one. I'll give standard error, okay. This is all the work you gotta do to get it. Not worth it really, if you ask me. So demand by weather and stack. This is not test related. Does anyone want to tell me what the degrees of freedom are for the two sample t-test? What are, like, how do you find them? The degrees of freedom for the two sample t-test are what? As I go and find them right now on the screen. I'm finding the degrees of freedom. And what are the degrees of freedom? It's too complicated. By that we mean it's a complicated formula, and I'll show it on the screen maybe. There are the degrees of freedom, 205.1336, and the degrees of freedom, there's the pooled t. I need to make that go away. And there's the degrees of freedom right there, and it did a better calculation. It's too complicated, and that's because the degrees of freedom two sample t formula is going to be the formula I'm showing on the screen. Once again, it's too complicated. Copy image address, so copy image. And the degrees of freedom formula is this formula right here. It's too complicated. What are the degrees of freedom for the one sample team? For the one sample t. We're not getting moved. I like that right there from Patrick Starr, it sounds like. What are the degrees of freedom for the one sample t? It's n-1. The degrees of freedom for the two sample t, technically with unequal variances, is too complicated. Now, do you know what the degrees of freedom are for the two sample t with equal variances? This is, you're going to hate me for this. But do you know what the degrees of freedom are for the t with equal variance, the two sample t with equal variance? This is not our class, but I'm just mentioning it so you can know. But when you do a two sample t with equal variance, and we go here and we remove this and we do the equal variance, remember what our sample size was? This is not our class right now, but I'm just showing you. The sample size was 413. So it's not n. Shameless plug for other stats, the pooled t-test. So you can do it, it's not n-1, because our sample size is 413, and it's a two sample t-test with equal variance assumed. It's n-2, which is also the maximum of our thing too. This is just a little theory for a half second. The maximization of this right here would be n-2 if these are perfectly equal. Like if we had a 200 sample size and we had perfectly equal standard deviations, the maximum of the formula we use is n-2. So our formula even equates to total n minus 2 when maximized with equal sample sizes and equal variance, equal standard deviation. When they start to get imbalanced is when you see a difference, especially the standard deviations really subtract from it a lot. A bigger balance in the standard deviations leads to a greater difference than n minus 2 in the formula. So once again, the formula is too complicated. Don't memorize the formula, but there are other ways of doing this and other assumptions that could be made. Our test has less assumptions, thus it is easier to use. This would have another assumption. Does everyone get what I'm getting at here before we do the output interpretation? That if you did a 2-sample t-test that assumes equal variance, you now have not 4, but how many assumptions or conditions to meet? You wouldn't have 4 conditions to meet. But if you do a 2-sample t-test that assumes equal variance, you don't have 4 conditions of random, 10%, nearly normal, independent means. You would now have what? You would now not have 4 conditions of random, 10%, nearly normal for both groups, and independent means, which are the 4 conditions. So I'm mentioning things important to your class. You wouldn't have 4 conditions, you would have 5. So you'd have 5, you'd have an additional one, making it kind of more, are you really meeting all your conditions to run it? Should you be doing this? So a lot of times people use the unequal variance because it has less conditions to run. It's just a safer test to do to not assume something. You see it says assuming unequal variances, which is a better default assumption to not assume that they have pooled variance, which is another topic. Let's talk about our output right here. You ready? Okay. So we already have the output on the screen, or did we not screenshot it? I don't think we screenshot it. There it is. Okay, so with the output screenshotted, let's go over to the confidence interval portion. Confidence interval. Tangent, man. I love talking stats. It's so, I love it. It's just so fun. There's so many cool things to know, and there's so many tests that can be done. There's just so much you can do with stats. It's a super powerful discipline. How do I copy this? Copy. All is love in the chat. There it goes. So once again, we want to annotate our notation. Does anyone know anything in the notation right here? Thank you, Cameron. Does anyone know anything in the notation right here? One thing you can do with this is you can write mu and mu above this, and you've actually written out mu rain minus mu no rain. You can write equal to 0, and you've actually written the null hypothesis. Even though we're doing confidence intervals, this portion right here can help you write the null if you see it, and know that you're doing the difference between these two, and that is the null. And the alternative, once again, would just be changing the sign, and the sign would be based on down here. If we have the does not equals alternative, the greater than or the less than alternative, and you would simply plug in one of these in this portion to write the alternative. So lots going on right there. Y bar 1 might, exactly, great job, Cameron, mentioning that the difference is y bar 1 minus y bar 2, and that is the difference right there. And this indicates to us that which of these means was larger. So since the difference is negative, what does that indicate to us? Since the difference is negative, which of those means is higher? Since the difference is negative, the second mean was the larger mean. So does this make sense to you logically? Just think about it. That means the average for blank days was higher on demand. What days had more demand on average? Just think about it logically. This means the on average these days had more demand. And then does it non-rainy days had more demand by about 900, more than 900. So now the next thing we see is the standard error of the difference. The standard error of the difference is a bit of a complicated formula. It's square root s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2, which is not in this output, and we did see previously. That output would have to be obtained from something like this. Can anyone tell me, since rainy days are the first group, what is rainy day sample size? Since rainy days is the first group, what is rainy day sample size from the output over here? Since rainy days is the first group, what would go here for n sub 1? Rainy days is the first group. Careful. I think that's the not rainy days, which is n2, the second one. And you can reverse them, but 112, yep, 112 right here. And then the standard deviation is 1665 right there. And so you'd put that right here on S1 squared. and then 301 is n2, and s squared right there, s squared sub 2 is going to be the standard deviation of the top. Does that make sense? Where they come from, the standard deviation of the first group divided by standard deviation of the first group squared over sample size of first group plus standard deviation of second group squared over sample size of second group. Square root of that quantity is the standard of the difference. Now, an important thing that happens is if you divide these two, you know, I'm going to call this section the confidence interval in the test because we're kind of combining this. We kind of just put this together. It's all in one output, so. If you divide those two, is the t ratio, exactly, the t with degrees of freedom that are too complicated to say. So if you literally divide these numbers, divide this, you get that value right there. And we can confirm this. It just always helps to show these things to know that we actually are obtaining these values. So we're going to go right here, put it in a nice good spot. Boop, perfect. And we'll go negative 907.1, and I said negative. There we go, divided by 186.1, and there's the t statistic right there. That t statistic, exactly where it is at, is plotted right here on this curve. Notice that the area below it looks like how much? The area below it looks to be how much of the curve? How much area looks to be below this? The area below it looks to be about how much? The area below it, very little, like nothing, right? And if you double nothing, because we talked about this a second ago in the other one, you still get about nothing. How much area looks to be to the right of this, which is not what we're calculating. We could do whatever test we want. How much area looks to be to the right of that? As in to the right of this is how much area on the curve? A ton, almost like 100%. Because now you're doing the area to the right of it, the t greater than. We'll highlight just that so you can see it. But if we were to do this p-value to the right of where we landed, it's right there, which is the area to the right of it, telling us that that is what is extremely likely by random chance, something at or above that. Something at or below that is virtually impossible by random chance. So where we landed on this curve seems virtually impossible to get something at or below, and that does not work well with that color. We have not used the mesh green right here lately. There we go. Something at or below this is virtually impossible by random chance. And we could test to see, yes, if the difference is less than 0. So we have chosen to do the less than test. Now, what would indicate to you that the difference, what is your first sign that the difference is probably less than 0? What is your first sign that the difference between these bike demands is probably less than 0? What would be your first indicator that the difference between these bike demands is probably less than 0? What is your first indicator that the difference between these bike demands, like on rainy days and not rainy days, 0 is not in the interval, and also, good job, Ethan and Cameron, the negatives. The interval is completely negative. So we estimate that the difference is somewhere between negative 540 to negative 1274. I'm gonna have you say it, ready? Go ahead and say it right here and see how well you can do on it. This is a tricky one. Give it a shot, write it in the chat, practice. Give it a shot, you got it. Yep, data is from Jump. Good to see you're smiley. Data is from Jump. Try writing out your I am blank % confident that the true blank is contained in the interval blank to blank. The color coding might not be perfect on this right now. If you're trying to color code it, look to what I'm doing now. There's your lower and upper. Ignore other things of same color. And here is your confidence level. I am 95% confident that the true difference between rainy and non-rainy days is contained in the interval negative 1274 to negative 540. And then you could add on the addendum, Cameron. I'd give you full points for that right there. You could say where it is estimated that non-rainy days have more demand. Because think how it's all negative. So you could add on where it's estimated that non-rainy days have more demand. But you said between rain and no rain days, perfectly with the context. If they take off points, I'd give them right back. So don't let them take off points when I'm like, that's a great answer. I always throw a little extra to be like, well, where we think non-rainy days have more demand. Like, what does the negative interval mean? We have good reason to believe that non-rainy days are where we'll see more demand. Because remember, the negative means it's a larger one. I am 95% confident the true difference between the means of rainy days and non-rainy days is contained in the interval. Boom, Valerie right there. Also, full points. If they don't give you those points, let me know. I am 95% confident the true difference between the two means of rain and no rain is contained in the interval. True mean, and then throw demand in there. I would give full points. Also, just throwing demand right there. The true difference in mean demand. I'd still give you full points. Throw mean demand in there. I'd be like, if they took off half a point because you didn't say mean demand. That's my now bigger qualm right there is we're talking about on average demand for rainy days versus on average demand for not rainy days. Does that make sense? So the smallest, no, you're worried. You're fine. Get some wows right there. Good work. So now we have to do the test right here to test to see if this difference is statistically significant. Why do you think we have evidence of a statistically significant difference? Why do you think we have evidence of a statistically significant difference? Because the null hypothesis is that mu rain minus mu no rain equals 0. What is not in our interval? I don't even care what I put alpha to. We'll put alpha to 0 is not in the interval. You got it. Put alpha to right here. Okay. So that's mu rain minus mu no rain less than 0. Go ahead and give it a shot. Longer thing to write out right here. I'll color code it again. Give it a shot, good practice. I know it's a lot to write out, but you get to the test, you get these points, and then you understand reject the null when the p-value is low. What does low mean? Less than alpha. What does alpha assume to be 0.05? What does alpha mean? The rejection point at which we reject the null. When the p-value is high, just let it fly. Don't reject the null. Means we don't have evidence for the alternative. Means we continue to believe what the null is. Doesn't mean we've proven it. Doesn't mean we know it. Doesn't mean we've proven anything. It means we didn't have evidence to go against what we currently believe. Only one more test to do after this, then we're gonna take a break. I'm gonna look at some emails, go to class. You mess with my hair. What do we have? One more test after this, the chi-squared. I do want to say this, please check out review 3. If you're watching this review right here and you're writing these out and you're practicing, hopefully you've watched the review videos. Lots of review videos up. I should have plugged them more, but they are more of just like a teaching video. This is your chance to write these down and to practice. Because one thing, if I tell you 100 times how to say this, it's another thing if you can do this. So we'll do the next question here in a second. I'm letting people. Quick question, is a university or some other institute behind the stream? YouTube randomly recommended this. I don't know how YouTube knows my statics exam is in 7 days. Well, Smiley, good luck on the statics exam. Yes, we are Stat 201 from the University of Tennessee, Knoxville. We'll play one of our fun intros right here. So here we go, Smiley. And then if you want to drop a question, let me know what you're studying on your exam. I'll play you one of my intros as they write out. So tell me it's something you're working on. Camera's right there, UT Vols. Here we go. Here's one of our intros for you. Check it out. Here we go. Yep, we got some written explanations in the chat, and Smiley right there. I just dropped links to all of our reviews for our tests. They have review practice tests on there. You can see there, go here for test 1 review, go here for test 2 review, go here for test 3 review. We've had people come here from Russia, New York, you name it. Calzone Tyrone, our friend from Russia, I hope he's doing well. It's global politics I'm not going to speak about, but lots going on in the world. So if you have a question about a t-test, a conference roll, you just let us know. I like Ethan right there. That went hard. So yeah, we're just here to do stats and practice stats and have some fun and talk about data and data analytics. So that's what we do here. So thank you for swinging by, Smiley. So this is the first random person we have had combine a little bit. Anyways. So great answers in the chat. I reject the null hypothesis because there is evidence which is shown by the p-value being smaller than the alpha level of 0.05. I have evidence for alternative that non-rainy days have on average less demand than rainy days. That is great right there because we're looking for evidence that the first mean is smaller than the second mean, as evidenced by the sign of the alternative right here. You can then use this to point to the first mean being smaller. Once again, we have evidence for that. Doesn't mean it is the case, just means we have evidence to believe that. Once again, the interval was completely negative, indicating to us evidence that the second mean is larger. So this could be reworded, evidence that the second mean is greater than. Do we have to put the average portion? Probably. Which portion are you talking about? Let me know, Valeria, which one you're talking about right there. What would the null in words be for this? The null states that the true mean of rainy days minus the true mean of non-rainy days is equal to 0. A better way to write the null, and a really quick way to write it, better or just easier I should say, is to simply write null hypothesis states that mean 1, mean of the first group is equal to mean of the second group. That's the same thing right here as stating that when you subtract these, they have no difference. If you just think about the algebra that takes place, I also got recommended this. Copenhagen Business School. That's so cool. What are you studying? Like what are you doing? T-tests? Are you doing Z-scores? Let us know what you're doing, and maybe we'll do one of those to end, Smiley, so we can do one for your class. Are you doing regression? Are you doing ANOVAs? Are you doing CANOVAs, MANOVAs, time series? I know a lot of topics we don't cover in this class. You might even be doing something I don't know, and it can be used to expand my knowledge on statistics. So I'm glad you like this, or I'm glad you're here. Maybe you don't like it, but cool. Copenhagen Business School. Shout out right there to you. Stats right here. I like Ethan's also in his recommended. Shout outs to Ethan right there. Okay, so we only got one last test, and you'll probably be doing this if you're in an intro course. The last test that we're going to talk about today is the chi-squared test of independence. So the chi-squared test of independence, ANOVA would be the one I have the most trouble. Oh, okay, let's look at ANOVA. We'll end with an ANOVA. Thank you, Smiley, right there. Maybe I'll help give you a greater understanding of it. We'll end the class with that after this example, because the last thing for us is chi-squared. Then we'll switch over to ANOVA, which is analysis of variance. So this is the chi-squared test of independence. The chi-squared test of independence. What do we need to do the chi-squared test of independence, which is one of the conditions? To do the chi-squared test of independence, we need what? We need what? You have to have this to do it. Hint, we're going to make a mosaic plot, contingency tables. You have to have this to do the chi-squared test of independence. Like I'm going to see if the weather is independent of it being a working day. We're probably not getting two categorical variables. There's cats in the chat right there. So it's not the most interesting of research. I might do something more complex, but this is weather independent of it being a working day. So when you write out the null hypothesis for the chi-squared test of independence, and there is no, you can do conference rules for this stuff, but it'd be a different thing altogether. But when you write out the null, how do we write out the null? So try writing out the null for this, and you can already see I've got some notes from earlier. How do we write out the null hypothesis for this? So try writing out the null for this. If you're in the chat right now, see if you can write the null. This will be so quick. So you look at your x. The x is weather. You look at your y. The y is working day. And you simply write independent between them. the chi-squared test of independence. So we'd have whether is independent of working day, and the alternative is whether is not independent of working day. Now, I always like to point to this example. And I didn't do it in class, so I wish I did. I'm going to let you pick between which test you get to take. You can either take test A or test B. And here is test B's pass rate from historic history. Here is test A's pass rate from historic history. So which test would you rather take? Which test would you rather take? Which test would you rather take? B. Some people say A because like, I want a challenge. I want to be the one who passes it. So I can put it and say I passed the hard test. But in this instance, you can see the difference in the conditional distributions. So you would think, at least logically, maybe A, though I like A, so you would see that the pass rate is higher and passing is not independent. It wouldn't change it. Good answer, Ethan, right there. Changing your X and your Y doesn't change it right there. I know a lot of people will do that. They'll be like, I'll take A and be the one who passes it. And I'm like, yeah, you could do that. You could do that. But what would the rock say about your choice between A and B here with such small differences? Now, I did do a difference there on purpose, but if this is the historic pass-fail rate of A and B, where we have A and B, for the most part, what? It doesn't matter. You know what the rock's always going to say. Over here on the far side, though, and over here, now the problem is it's not always cut and dry like this. Because sometimes we run into the world where there's a gap between it that looks like this. So really what we're analyzing here is these differences between conditional distributions, and we're asking, is that a large difference, unlikely by random chance, small p-value, or is that a small difference, likely by random chance, hence high p-value? The greater the gaps in the conditional distributions between x and its y variable of interest, the more evidence there is for the alternative, i.e. smaller p-value. Does anything I've said there start to make sense? And I'll repeat it again. If you've been following along through the whole semester, that whole put of words together, that whole barrel of words might make some sense. The conditional distributions within the mosaic plot, when they have large differences, gaps between them, are more evidence for a dependency, i.e. it's not independent, which would mean we have evidence for the alternative, i.e. small p-value. The closer they are together, the less evidence there would be for the alternative. And if there's less evidence for the alternative, we fail to reject the null because the p-value is higher than the level of alpha. If that's starting to make sense, you've been following along. And so now we go and look at the results of this test. There's a lot more to this. I'd be teaching the whole chapter, so I encourage you to watch our chapter reviews on this, found in Review 3. But go check those out under Review 3. And I can't plug this enough if you want to see more in depth and to see an example walked out step by step, which I do under the review. And just so you know, I'm going to go plug it right here and show it. Please check out, and I'll even put this video, because I'm not doing all the steps. I'm just talking about how to do the test and the results. You want to go down here to the end, go to this chi-squared test of independence, and you will literally see me do a 25-minute example, no jokes, talk through when we use it, show how to do everything, all the steps, step by step, all the calculations, and that video can be found right here. Once again, I like to do these differently every time we're doing it so you can get a little bit of a different idea of how to do it. You have to teach things and learn things different ways. It's like working a muscle. That's not how you work out, right? I don't know. I don't work out. So with this, let's go to the results right here of the test and see what we get. So when we do the chi-squared test of independence, the p-value is with the Pearson. We don't do the likelihood test. We do the Pearson chi-squared test. Now the chi-squared, like the t, has what? Just like the t, the chi-squared has with it what's? What commonality do the t and the chi-squared have? The t and the chi-squared both have what's? The t and the chi-squareds both have what's? They're different distributions, but the t has this, n minus 1, or a too complicated formula, and the chi-squared has this. Degrees of freedom. Degrees of freedom tell you the shape of the distribution you are using. Even the f, which is used for an ANOVA, has degrees of freedom. The f, whoops, child, I did over there. What's so interesting is that the f distribution has with it two sets of degrees of freedom, and it's the ratio of two chi-squareds. So that's just some fun facts of the day. my gosh, I can't type my commands in. So we're going over here to the t-applet by way of getting to the chi-squared. My chi-squared command should also be there. And we go here to chi-squared applet, and we don't have an f on ours, I wish we did, but you can see the chi-squared becomes more normal, and there you go right there. I guess I should have asked Adam to program an f, but I think he did. We got chi-squared up there. That he did. Nope, not there. I'll spam bar to do that. I want to see his code behind that. It's really good. And so with this right here, all we have to do with this output is know a few things. At least with this output. There's more to the chapter, but let's talk about this. How do we get the degrees of freedom? This is rain, no rain, holiday, yes, holiday, no, working day, yes, working day, no. This is a 2x2 matrix, so the degrees of freedom are what? What are the degrees of freedom? Since it's 2 rows and 2 columns, like 2 rows and 2 columns, drop 1 right, 1 times 1. So it's 1. Ethan, it's really easy, right? It's 2 answers to 1 and 2 answers to the other. It's a 2x2, rows minus 1 times columns minus 1, 1 times 1, and the answer to the degrees of freedom is 1 right there. So it's 1 degree of freedom, also seen in the output. Now the chi-squared would be the sum of all the cell chi-squareds, and found by the observed minus expected squares over expected. Do know how to use these formulas. Please watch the reviews where I go more in depth on observed minus expected squared over expected is a cell chi-squared. The sum of all the cell chi-squareds, the Pearson chi-squared right here. That's the sum of all the cell chi-squareds. The worst sum thing I've ever written. And the formula, so the sum of all the cell chi-squareds is the Pearson chi-squared, and that leads to the p-value. Expecteds are row total times column total over grand total, and that's it right there. How will we calculate the Pearson chi-squared by hand on the test? We could give you output like this. Let me show you. If you received, did I delete it? No, it's right here. If you got the following output, take a moment, really good questions right here. Show me how to get the Pearson, use the values on the screen to get the Pearson chi-squared. Use the value on the screen, the values on the screen to get the Pearson chi-squared. So try using the values on the screen to get the Pearson chi-squared. I'll drop some hints here in a moment. Use the values on the screen, so you have to know what you're looking for. There's a lot on the screen. Use the values on the screen to get the Pearson chi-squared. Don't just type the value. And how'd you get that, Cameron? I think Cameron might have done the steps needed. So now it's obtainable. So what we would do is we would do add up all the cell chi-squareds. Exactly, you got it. You notice I'm going to the cell chi-squareds, which is the bottom box, and adding them all up. And there it is right there. So, yep, great job, Cameron, getting that extra decimal after that. Find this expected count. So let's pretend we have this output on the screen. This is a really good review right here. So find this expected count. I'll show you a trick too. Great job. You want to know a trick? Other than doing this, do you know what the expected counts add up to? Watch this. You ready? You're going to have a total wow moment right here. 301 minus 202.6102. There's the answer. Because if you add this value right here to this, you'll get this total. Or if you add it to this number right here, you'd have to get this. So we could check and do 36.61017, and you get that right there. So whatever goes right here has to mathematically add up across. Now you want to do this formula I've written right here, which is 135 times 301 divided by 413, and there's the answer. But then you could double check it by adding it right here, or whoops, see, then I do a typo like that. Does that make sense? Valerie Season's like, wait a minute. Or you could add up all of them and subtract out of 413. So you could go 413 minus 202.6102 minus 36.61017 minus 75.38983. And there's the answer again. Because the expected counts have to add up. Oh, I'm zoomed in, but it worked. Sorry. The expected counts have to add up to the totals across. They work the same way as the observed. So you should know counts are also observed. A lot of people ask, where's the observed? They're the counts. So that's a synonymous phrase. The cell chi-squareds, go ahead and find the value in cell B. Now, if you knew the Pearson, the chi-squared test statistic, which is the Pearson chi-squared, if you knew that is equal to 1.1833, you could also cheat and find B, but I wouldn't. I mean, you could, because if you know that, you can go 1.1833 minus, this could be a double check. I would not probably try to find it this way initially, because you only know this because you have other answers. It's not how it's found, it's just a backworking. But how would we find that value, which you could then find it that way or double check it, but find the value in value B. So a cell chi-squared is the formula observed minus expected squared of this quantity to make it positive, standardized by the expected, is equal to a cell chi-squared right there. And so now we need to take the values of what we observe divided by what we expect, or minus and then divided. And so, there we go. Plug in the values right here, make sure we do it. And 80 minus 75.38983, square this, get like 21. Nope. Why did square root? There we go. That's why you always think through it in your head. And then divide by expected, 75.383, 0.21, 0.2819. There we go right there. So hopefully that makes sense. Now we get to the interpretation of our result. So now, when we get to the final part of this, what are we going to say? I what? Awesome. Well, thank you so much. I'll mention just a tiny bit on ANOVA. Check out this video. It's still up later if you want. I'll just briefly mention ANOVA because it's pretty cool. But have a good night. Have a good afternoon. Copenhagen shout out right there. So with this, what would we say to finish off? Last thing for us, then we'll mention just a tiny bit right here. I love it when we get people swinging by here. So what would we say right here? I mean, any reasonable level of alpha. So I would say I fail to reject the null that working day is independent of rain with a p-value of 0.2767, which is larger than my value of alpha, which is 0.05. This means I do not have evidence for my alternative that working day is not independent of alpha. And good work. I'll mention ANOVA right here. We'll end with that. We've gone right under 2 hours today. So I'm putting not stat 201 ANOVA. Okay. Anyone say this in the chat so people can see? An ANOVA for our class is what? Anyone wants to put this? This portion right here, this video, is not stat 201, not on test 3, Do not study this. Like, do not study. I mean, you can if you want, but not on test 3. I'm just waiting for someone to be like, I studied in ANOVA. I learned what an ANOVA is. Not on the bad boy. So there we go. An ANOVA stands for analysis of variance. It's actually super important because an ANOVA is actually doing the t-test repeatedly. So an ANOVA, which one way you can use it, can be used for other things, can be used to analyze the difference in what's not just two means, but an ANOVA can be used to analyze the difference in not just two means. Well, actually, it can be. Thank you, Ethan, right there. An ANOVA can be used for two means, but it can also be used to analyze more than two means. Do you know what the null hypothesis would be for an ANOVA? It's not that the two means are equal to each other. Just take a wild guess for an ANOVA. The null hypothesis for an ANOVA is not that mean 1 equals mean 2, because that's the two-sample t-test, which we covered. But for the ANOVA, which has more means, the null hypothesis would be what? Not that mean 1 equals mean 2, just state it in a quick fashion, because we're just saying the means are equal for the first one. So the null hypothesis for an ANOVA would be what? I bet someone's going to get it. Like, if you didn't know anything about days and demand, you would just assume what about days and demand? That the demand is what for all days? You had like 10 more seconds. The null is that all the means are equal. That mean 1 equals mean 2 equals mean 3, that's exactly it. All the means are the same as the null. And now the alternative is that at least one mean is different. Does that make sense? The alternative is that at least one mean is different. Now, what we have in an ANOVA table, I'm going to make an easier ANOVA table. Where's my Survey 10 data? Don't I have Survey 10 data on here? I hate how big these numbers are. Oh, there it is. I just saw it. Here's Survey 10 new. Like, I got it. So what this means is I can do an ANOVA instead of a t-test. It's where we do the pooled variance. So it's doing a t-test, but so watch this. Analyze fit y by x. Does gender explain people's heights? And now we do the ANOVA instead, and we get the following output. And here's the ANOVA table. But I want to point out something really interesting. Sums of squares. We heard of sums of squares in regression when we talked about the sums of squared errors. Error is another name for what? In a regression, an error is another name for what? Think of an R word. If I say sums of squared errors, then that is another what word? Think of regression. Sums of squared error. The squared error is when we take the what and square it to get a quantity of how far we are away in regression. But you can do the same thing for points around the mean. A residual. So think about this. This is how much we have not explained because it's the error. This is how much we've explained out of the total variation there is to explain. So if we take how much we've explained out of the total variation, what value am I calculating by saying we have explained this much variation out of the total variation? What value did I just calculate by finding out how much I explain out of the total variation? What value did I just calculate over there on the left side by figuring out how much I explain of the total variation? How much did I calculate? Ethan is. Great job, Ethan. I just found out how much variation gender explains. This is what it didn't. That's the error, which is how much it misses. So the total amount of explained variation out of the total variation, which was 13,000-ish, That was 7,000 explained. 6,607 remained unexplained. So this is how much I explained out of the total variation. The value I calculated is what? By finding how much variation is explained. No worries. Once again, not on test 3. But think about how this connects to regression now, because the amount of variation explained out of the total variation is just r squared. R squared is what percent of variation was y is explained by x, but we can still use height to explain gender and talk about the amount of variation explained in height by gender by calculating how much error there is and how much we've explained out of the total variation that exists from the naive model. And that's a topic for another day right there. The degrees of freedom relate to how many explanatory variables there are. Since gender is a 2-level categorical variable, it only brings with it one indicator from the grand mean, longer talks, but gender, 2 levels, so only one indicator, 1 degree of freedom is used. That's how many variables are being used. The error terms would be, there's 699 points of data, so we take out the one error term, we take out the one estimate, and we have 697 other estimates for the remaining error terms. Does this? I mean, not so much really. The sums of squares is a lot to calculate, but when you do the mean, you would divide this by 1, you would divide this by 697. So the mean right here is on average per degree of freedom. Does that make sense right there? So this portion right here, the mean is on average per degree of freedom. So now you're doing like, okay, so since gender only has 1, we divide that by 1 and we get this. And then we do 607.879 divided by 697, and there's 9.48. And so additionally, the F ratio is a ratio of the two numbers. So all you have to do to get the F statistic is divide what you observe over what you expect. There's the observed over expected, because we observed this much being explained versus expected due to residuals. And that leads to the F statistic, which is literally just those two values divided right there. So divide that by that and get the F. The F works like the chi-squared. It's the ratio of 2 chi-squared. So a very large F statistic leads to a smaller p-value. And we could go look at an F distribution and see where this lands to plot it. But the p-value is basically 0. And think about this. You could state that gender is, has no impact on people's height. We're not saying it causes people to be tall, but there is evidence to suggest that gender is a good explanatory variable for height. But any questions this is a bit advanced. The chi-squared has 2 degrees of freedom. It has numerator and denominator degrees of freedom, or the F has 2. F distribution, Matt Wagner. Ripping up like tape over some. Oh my God, there's his dog. Where's the F? There's the F. 1,698, and it was something like, it was ridiculous. It was like, doesn't even plot it so far out. My head, but instead, no worries. But this is just another test that can be done. I did it so briefly. I didn't go into great depth on it. I didn't show how all the the naive model calculates the sums of squared error. Yeah, no worries. I'm glad you enjoyed it. I really appreciate it. I'm going to take a break here, but thank you so much, everybody. Once again, this is not on the test. I mean, 2 sample T is on the test, but not the ANOVA. ANOVA's not on the test. But fun stuff to talk about. Good topic, ANOVAs. Really would be one of the next. If we added some of this class, it'd be an ANOVA. Not too bad. But with that, I will pop in next semester anytime. Swing by the office, say hey. We give out some T-shirts today. With that, there's an intro I can't play anymore. It actually has copyright music on it. It's the all crazy in the studio one. I got hit with a copyright claim on it. With that, we'll play our fun outro thing here. Till next time, thank you, everyone. Let me know if you have questions. I'll be answering emails. Bye for now, everyone. Bye. That's the wrong button.